Okay, so now we are going to write our first device driver module. And to be able to do that, we have some prerequisites or preconditions. And that is that your multipass instance should be running and VS Code should be connected to it. Now, to what I have on my screen here is a terminal screen. And then in the background, there is VS Code. And I'll just quickly show how you can go about starting the instance and connecting to it. So my primary instance here, the virtual machine is stopped. It's not running. So first I have to get that running. So I'll do multi-pass start primary. It should take few seconds to start. Let's just give it few seconds. Well, it's actually taking longer than I anticipated. So okay, perfect. So now if we do multipass list again, we should see that primary is in running state and it has got an associated IP address. Now recall that we had used this IP address in VS Code. By the way, we do not need this terminal anymore, so we'll put it in the background. So we'll come to VS Code and under this remote explorer, notice that previously we had connected to primary and the IP address was exactly this. In your case, the IP address might vary, so that's fine. But we want to connect to the LDD directory. So I'll just go ahead and click on this arrow here, which says connect in the current window. And once it is trying to connect, it asks me for password. The password was P. That is the password I had set. You could have set something else. And also, if you don't readily see this terminal, what you can do is go to the menu, go to terminal and click on new terminal. So we have new terminal here. Let's just pull it down here somewhere. No. Okay, let me again do that. Uh, Orange, new terminal. That's fine. We'll work with this. So right now we have no files here. And also at the bottom, it says SSH 192.168.64.12, which is the IP address of our machine, the primary machine. So we're all good now. Okay, so now what we are going to do is write our first module and just kind of print hello world. And then we'll kind of tease apart all the parts that were involved in compiling it. Why was it written the way it was written, and also what the Makefile does for us. Okay, so we need two files. I'm going to call the first one ldd.c because Linux kernel modules are written in C. Lately there has been support for Rust also, but we will write the modules in C. All right. So the first file we created was ldd.c. The second file we want to create is Makefile, and please ensure that the file starts with an uppercase M, not a lowercase m, not like this. It has to be exactly this. Right. All right. So we have these two files and we have our terminal. Let me put our terminal on the side here. Perfect. So within the C file now, let me just cheat and copy paste, some bits here. All right. So I have approximately copy pasted, 18 lines worth of code here, right? 18 code lines. And we will come to what these lines mean in a while, in a bit. And let's go ahead and save this. And then let's go and populate the make file. So in the make file, let me also cheat again and copy paste. So I've copy pasted about 7 lines here. Let me, oh, just a moment. Um, let me reduce, yes. Okay, so now coming back to the ldd.c. So our intention is that we are wanting to write a kernel module that can be loaded into live kernel, right? And my claim is that the 18 lines here are good enough for a hello world program. And uh, this piece of code here goes on to explaining, or we'll kind of, take a look later once we have tried the experiment, that this goes on to explaining the idea of what I was previously referring to as constructor and destructor. So what you see on screen, the code is for constructor and destructor, and what this is and why this is useful, that will come to also. But just kind of for now, take it on faith, or just trust me that this is the bare minimum to be able to write a module that the kernel can accept. And okay, then let's go ahead and uh, talk about these two files. So we have the module related code here, and we have the compilation code here. So we would want to compile the code to become a kernel module, and that uh, is done using the Makefile here. Now, for those of you who do not know what Makefiles are, well, these are just a way to automate, right? And we'll talk a lot about these in a while, but just for time being, know that Makefile is for automation. It helps us run commands, like bunch of commands automatically. And then the ldd.c is where our kernel module source code is. All right, perfect. So if you're able to follow through this much, let's just go ahead and kind of compile the code. So I'll just in our terminal go ahead and do make, and if you see, it went ahead and printed a lot of messages, did something, and also it has created like tons and tons of files here, right? Okay, watch this again. So if I do make clean, it will kind of wipe out all the extra files it had created. uh, so right now, then on your screen you only see the two files that we had created. But if I do make again, notice that it has created like bunch of files, and of these files, of all the files that it generated, the ldd.ko is what is of use to us. That's the actual kernel object or kernel module, right? And so far, this is what we have done. We started off with a .c file, and this is where our source code was. Then we kind of compiled it and created a ko. The claim is this is the kernel module. And the next step that we want to perform here is to inject this kernel module into the kernel. And then after that, verify. Verify in the sense whether or not kernel accepted it, right? Okay, so then the way we do that is we call a utility called insmod, and insmod is the utility that will take your kernel module and inject it into the kernel. So let me then uh, submit, or provide it with the name of the module, and it has to end in a .ko because it needs to know name of that object file. All right, so sudo insmod ldd.ko. Things seem to have gone well. If I do echo $, that essentially prints the status of the previous execution, and 0 means a success. So this command here was a success. So the next thing we want to do is verify that our kernel module was injected and accepted by the kernel. So my claim now is we had two functions here, which again we'll come back to in a while, but there was a print statement here and a print statement here. My claim is this is the print statement we should see, but see where. So what we are instructing the kernel at this point is do a print somewhere of this statement, and that somewhere happens to be the kernel log buffer. So we now need to somehow go and print this log buffer somewhere here, so that we can see whether or not this was printed. Right. So the kernel internally in the memory is maintaining a log buffer, and it continues to print there. And what we instructed using this print k function here was to print this in the buffer. Right. And that will be one of the hints in which in which case we can confirm that our module was loaded. So then the question is, how do we go about printing that buffer? And the way to do that is we type sudo and and execute the utility dmessage. Dmessage essentially will print the kernel messages for us, the kernel buffer. All right, and so we have a lot of things printed here, and at the end of it, we do see, hello world from in pajama, and that is same statement as here. All right. And then we also see corresponding to LDD colon, LDD is name of our module. So it is printing something else. It's like loading out of tree module, taints kernel, module verification failed, signature, blah, blah, blah. This will fix later on. But the important part is that the kernel accepted our module and it went ahead and executed this function. And why this function, that also will talk about in a minute. So now the module is in the kernel, and let's say we want to plug it out. So how do we kind of uninstall or remove the module? So for that we have sudo rmmod and LDD. So we just have to give the name of the module. We don't have to give the .ko this time. If we give .ko, that is also fine, but that is not required, strictly speaking. All right, so sudo rmmod LDD, and now we go ahead and print the D messages again. And now um, if you see this message is what we have printed, right? So what the kernel has printed. So somewhere then it should ring a bell around the fact that whenever we insert the kernel, this kernel module into the kernel, whenever we insert it, this function was called, and then whenever we kind of remove the module, this function was called. And then somewhere this kind of relates to the idea of constructor and destructor, right? And we'll talk a lot about this in a minute, but all of this here is just kind of some header files, some macros. Similarly, at the end here, these are some C macros, and these are the only two C functions that we have written, right? And now let's go ahead and talk about which file means what and what things mean what. So okay, let's get this on the side, or actually let me just put it here. Let's go here. All right, so what part of the code is doing what? Okay, so the kernel requires that each module have in it a function, right? A function that the kernel can execute once the module is injected into the kernel, right? And so that we call the init function, or referred to as the init function. So again, the idea here is that when the module is inserted, this is the function that the kernel is going to call. And what does this function typically do? It's supposed to kind of set up some bookkeeping information, register or create a queue, something of that nature. Anything that the core functionality of the module will require: memory, queues, events, registering for events with some other module, so on and so forth. That goes into the init function. Now, similarly, when the module is kind of taken out of the kernel, then it needs to execute some sort of a cleanup function or exit function or release function. I mean, these are the different names people refer to it by, right? Typically, common ones are cleanup and exit function. So similarly, there has to be then a function that the kernel can execute once we have instructed it to kind of remove this module, right? And what kind of functions or what kind of functionality does the cleanup function have? Well, it can do cleanup related tasks like freeing up the memory, unregistering for events, returning back the resources, gracefully shutting something down, and so on and so forth, right? Those kind of things are part of the exit or cleanup function. And now what you see here is we have this one function, right? It's an int type, returns an int, which is 0 here. So the idea is if something went wrong here, if it was not able to, get the resources that it required, it should return like a negative number, some error code, and then the initialization or insertion of that module fails. That's the idea, right? So it will essentially, uh, you know, return like an integer number. And then the name of this can be anything that we please. So there is nothing sacred about, pajama underscore module underscore init. It could have been just as well XYZ. That's completely all right. Then the function implements the body. In our case, we only printed a statement, right? Okay. So that was about, one function that we wrote. The second function we wrote, well, it doesn't return anything because, the cleanup, if it fails, the kernel is left in like a bad state. No, but, and cleanup is also like the last thing to be done. So again, the name can be anything here. Nothing sacred about pajama underscore module underscore exit. Name can absolutely be anything. And the init function doesn't take any parameters, and so does the exit function, because there is kind of, well, at least known to me, there are no inputs passed to these. So, the input type or the function parameters are nothing. So void. Okay. Then there are two lines here which are very special, right? And if you see, the name that is used here must go here, and the name that is used here must go down here, right? Exit and init. So, what are these? So essentially, the kernel needs to know what function it needs to call as part of initialization. It needs to have that function pointer, so to speak. And similarly, during exit or during like removing the module, it needs to know which function it needs to call to perform that exit. Where is that recipe? Right. And so these are two macros, right? And what these macros do, we'll tease this apart in later videos, just so you understand all the details, internal details. But take it on faith right now that this is a way in which the like during the compilation process in the .ko file, there are two symbols exported, right? The pajama module init and pajama module exit, right? These are two symbols that are exported, and while consuming that ko file, the kernel can identify, oh, okay, I'm supposed to go after this function when I'm trying to inject this module, right? Or insert this module or consume this module. I'm supposed to go after this function. And similarly, when exiting, I'm supposed to go after this function. So these two function call like thingy here. Let me clear the screen now. So these two function call like thingy are actually C macros, right? And that is why they can be called from outside of a function. Otherwise, a function call requires that you call it from within another function. These are lowercase, function like looking, but they are not function calls. And also, I think I should go ahead and change the theme a little bit here because it's not very evident. uh, Let me choose a familiar theme. Maybe I'll choose like this. So the other thing I want you to notice is that there are semicolons here, which in my previous theme wasn't visible. But rest assured that there are semicolons. But these two, again, are macros. These are macros, and so are these. So these macros up here, by the way, also I should mention that these two macros at the bottom line, 17 and 18, come from, these header files. These header files are required, and these header files are required for these macros and these macros. Okay. And then what are these macros doing here? So these macros are essentially helping us specify the license that this kernel module is going to be released under or is available under. And there are like various licenses, but we are using GPL. Okay, why this is important, and this is mandatory. If we don't have this, the kernel will not accept this module. I can go ahead and do like a demo of that in a bit, but this is mandatory, right? And okay, why is it? So the kernel then has modules internal to it, various features, and those features might be in like, let's say MIT license, GPL, Apache 2, so on and so forth. Now, the thing about the GPL license or the licensing terms is, if you are using a permissive license, you will be allowed to use the feature from other permissive license, right? And then there is like a hierarchy of which license allows you to use which other license and so on and so forth. But the idea is, if let's say we use like a restrictive license here, then the functionality from the other permissive license will not be available to us. So if you don't plan on releasing if you don't plan on releasing your source code to the public, let's say, under the GPL license, then you're not allowed to use other functionality that's available as part of the GPL license, which is marked as GPL in the kernel. So then specifying which license you're using becomes absolutely important, so that the kernel can allow you to access resources or functionality that are released under certain licenses. And you can search and look up in terms of like which licenses, like writing a module in which license allows you access to which other functionality in which other license, right? All of that is available on the internet. Then these two macros here are optional. If I did not put them, that would be all right. But what's happening here is, I'm just saying that, hey, the author of this module happens to be, having this name here. And then I'm describing what this module does as one liner, right? That's about it. So what happens here is, people can understand some description, or the kernel can record and print some description, so that other developers can understand what your module is doing, and also they can reach out to you in case something goes wrong or something needs to be improved. So these two macros are essentially for that. Now with this, let's first quickly try out an experiment wherein we do not provide this line. And also let's get rid of, actually first, let's get rid of these lines and let's have this. Let me then pull up the terminal. Then we do like a make. Okay, so the module is built. Now we do sudo insmod ldd.ko, and then we do sudo 𝘁𝗵𝗶𝗀, right? And at the end here, we again have hello world from 𝘁𝗵𝗶𝗀. And also notice that the kernel did not uh, complain about anything. So now we'll go ahead and do sudo rmmod ldd.ko. Again, the ko is not important when removing, but we'll just go ahead and try that, right? And if you see again, the module is removed. Now, allow me to introduce another command here, which is sudo dmessage, actually an option to the command. So sudo dmessage printed the kernel log. And what we're going to do now is say use -c option. And what that does is prints the kernel log and also clears it. So next time we do dmessage, it'll print nothing, because that buffer is completely clean now. All the logs are printed and the buffer is clear. And this will be helpful when we specifically want to see prints from our module. And let's say if your kernel is very noisy, then it keeps on printing stuff, and then somewhere in between that you will have your prints. To get rid of that kind of search, searching between the noise, we can clear the kernel buffer. All right. So now let's go and comment this line out here, the fourth one, the module license, and then try and do make clean to clear everything out. Then do make again. So we built our kernel, and as you saw, or as you see, not saw, but as you see here, it the compilation process itself fails and says, hey, I see a missing module underscore license, so it cannot compile further. So the kernel, or rather the build process, enforces that we state uh, and a license, and once I specify the license, the compilation goes through. Now when I'm going to do, let's say, insmod and then do dmessage, you'll see that there is only one line, and this was because we used dmessage minus c. I'll go ahead and do rmmod. Oh, actually, before that, now if we were to do mod info, or info mod, I think, um, info mod ld.ko. Okay, let me find out the command real quick from my cheat sheet. Okay, so it is mod info. So mod info ldd.ko. So if you see, it kind of uh, prints descriptions, right? And then there is it prints the license, it prints like the name, what path it is available at. This is some, source version, something, the name of the module, and some version magic, right? Now, what I'm going to do is enable these two lines. And let's go ahead and also remove our module. Remove the module. Let's do dmessage. Yeah, so we also see the goodbye message here, which is perfect. Now we clear the logs. So now when we do sudo dmessage, nothing's there, which is perfect. Now we'll do make clean, do make, and then we go after mod info. Notice for using mod info, we don't have to have the module inserted. It's just that we need to have access to the KO file. And once we have that, it'll go ahead and print information. And as you can see, it's printed the author's name here and also printed the description that we gave as part of this macro. So that then is a bare minimum code that we need to write a Linux kernel, a kernel module. And then in the Makefile here, this deserves like a video of its own, but I'll quickly explain what's happening here. So the kernel comes with its own build system, right? So this is like a complete set of tools, automation, all of that. And somewhere we are injecting or providing it with information through our Makefile. Right, we are providing it our Makefile, and then kind of triggering it to launch this build system, and as part of doing many things, build our KO. And many things, I mean, doing generating like all of these different files here, right? And what these files are, again, we'll come to those later. So this object minus m plus equals to ldd.o, essentially we are saying, hey, we want you to create an object which is called ldd.o, right? And as part of this, as part of creating this here, the kernel will end up creating this, which is of use to us. But then we are instructing it that, hey, go ahead and include in the list of modules that you're going to create, just append to that this one module, right? And then we have two targets here, all and clean, and by default make executes the target that is on the top. So if we do make all, that is same as executing this target here. If we do make clean, which we have done a couple of times, then it executes this command right here. And in that sense, make make files are a way to automate commands. All right, so what is happening here? So this make command internally calls another make command. It says, okay, change the directory to wherever the kernel's build tree is, right? And this here is dynamically filled in. Okay, I'll show you that in a while. This is dynamically filled in, but we say, hey, change the directory to this. Then, by the way, the modules are supposed to be output into the present working directory, which happens to be this directory, this directory right here, right? And then we are saying, hey, go ahead and create your modules, right? So our make internally calls another make, changes the execution or changes the working directory to this, which belongs to the kernel, then says that, hey, make sure that you put the output in the directory that the original make was launched from. And oh, by the way, you're supposed to create modules, right? So this is what the make command is doing. And then, or rather, the simple make command that we launch internally launches another make, something, something modules, right? And then the clean here is essentially saying, hey, again, go back to, change the working directory to this, ensure that the modules you're looking at are from the current working directory and execute the clean command, right? So let me quickly show you the output of all of this, right? So when we do let me do make clean first. So if you see, it executed this command. Let me actually get rid of this. Yeah. So it executed this command make-c, which is similar to this or exactly matching. Then lib modules. So this right here uh, is make executing a command line command, getting the output of it and putting that output here. And the output for this command, the uname-r command, happens to be 6.8.0-35-generic that you see here, /build, right? And then in like m equals to, it has substituted the path for the LDD, which happens to be, so if I were to pwd here, which happens to be home/home/ubuntu/LDD, that is here, and then clean. And then as part of this, make has, the build system rather has gone ahead and cleaned up the source code, right? And so all the files that were generated here disappear. So now when I do make then, or make all, both are same. If I do make, then it will go ahead again, change the working directory to the kernel's build directory, point the modules or output of the modules to /home/ubuntu/LDD and create or execute the command modules. Then it goes ahead and, does a lot of things. And then as you can see here, it's generating different files, right? So this then, 7 lines worth of automation here and 18 lines worth of code here are the basic essentials to even get started with being able to write a kernel module. And in the next videos, then what we'll do is explore all the utilities that we used, dive into like little bit details of the kernel and how it operates, and then from there we'll go towards writing or adding more functionality to our module. I'll see you in the next one.